It could help improvement. Still, it's unstable. You know what we do. How many do you?
Somewhat. I sell them at work, but I work for myself, and I'm not actually allowed to buy tickets. So it doesn't show you what you at home.
Well, I can take a book to the observatory. Oh, yes. I'm one. You want to buy some sit yeah, but, well, it was 100, I don't remember that.
Right.
Well, good evening, everyone. So welcome to February's RASC Victoria Center meeting. I know we have a couple of visitors here. Any other new members or visitors? Welcome, thank you. So welcome to the visitors and new members. My report is in the Sky News. They may well have the distinction of being the briefest and least meaningful president's message in the history of Sky News. I think everything that we tried to do this month was canceled because of the weather. It was awful. I mean, I probably reported all kinds of fun stuff we did. I couldn't think of anything because it was just canceled one after the other. And just a reminder that coming up this Friday, we're scheduled for the 32-inch telescope here at UVic, and the weather's not looking very good. So we'll try and send emails as soon as we can, but it's not great. Stephen Courtney has a little presentation for us briefly just to start on here. So we'll let you go through.
I've expanded on my ecliptic calendar and I've created just the latest star map that shows the whole sky. And I've got several such on it. I've looked at the message on the right. Some appreciation of what it's about. So basically, it takes the 20 brightest stars and finds where they are on a single map. And the calendar, I don't know if you've seen it over the years when I've presented it, but it's designed to simplify the subject of stargazing and to the common person as far as understanding what's going on. So the whole sky is represented in one view. And some people in one know that I've also tried to understand astrology at the same time as I understand astronomy. And so for me, this calendar is a way to bridge between these two subjects in a way that we can have some understanding and we're on the same page. So this is a map that shows you where these, as we speak. I made it today. So people are having trouble. So the calendar couldn't be simpler as far as showing one map and allowing everybody to sort of have that appreciation of the objects that are moving the planets and along the orientation of the ecliptic plane is also exceptional within the star maps I've looked for and checked out. So to get the big picture to where this is showing everything that's in the sky, and then the Earth is in the middle. The difference here is that it takes the Earth and thinks of it as one point of view, and that you have the spherical dimension of the Earth looking in at the Earth, and then you have a spherical dimension looking out from the Earth. So just as we can make a Mercator projection of the Earth, this is a map of looking in at the Earth. And it has the difference to the regular Mercator projection is that it takes the equator and turns it into the sine wave. And then all the longitude and latitude lines conform to that orientation. And therefore it gives you what looks like a sphere that has been rolled flat rather than the Mercator projection that we see where everything's at 90 degrees straight lines, longitude and latitude. And you don't get a sense that you have a sphere that's been opened up and flattened out. You can also see that Greenland is to scale compared to the usual Mercator projection blows Greenland out. But so there are areas of this map that are very to scale, and there are areas you can tell by the distortion of the sphere that, like Siberia and Alaska, are pretty stretched out. So the same thing's happening with my calendar, where you're looking out from Earth as a singular point of view, and the planets are oriented to the ecliptic plane, which runs through the center. And because this is a cosmic clock, it's divided into the 12 signs of the zodiac, which is different than the 12 constellations. There's a lot of confusion between astronomers and astrologers over that particular point. This map shows the 12 constellations of the zodiac, and the 13th, which is often brought by astronomers, is Orpheus as the centaur. And some people rock the astrological world by saying that, if you thought you were a Sagittarius, you're actually a Capricorn, or was it the other way around? But that's because they're looking at the signs rather than the constellations. The constellations are different sizes. You can actually be in the constellation of Leo and still be in the sign of Leo, but for the most part, they're all set. Anybody have any questions?
How can we get a few of those? They're actually coming handy for like on the hill during summer Saturday evenings. Or because your laminators are kind of dew resistant, but they're kind of a neat at a glance sort of map of the sky. So how can we get a few of those?
Well, you just have to contact me. It'd be easy. I've got a website. I can give you my email address. Everybody finds the subject pertinent.
Leave your email address with us, with Les, and we can put that in minutes. And, already done? Yeah. Great, thank you. No other questions for Stephen?
It's a lot of work you have done.
Yeah, started in 1980.
Okay, thanks, Stephen. Just a reminder that our librarian is cleaning out our library upstairs after we go up for our coffee and cookies, and he's got several hundred books just to give away. They're books, I think he said between 1950 and 1980 or so. I think he's got 2 or 300 or something just to give away. So you get first dibs. If you want to come up afterwards when we go for our coffee and cookie afterwards, come on up and have a look and just help yourself to whatever books that you like to take home with you. Otherwise, we're going to have to dispose them or give them to a charity or something. But by all means, come up and have a look, take what you like. And also, we now have a book page for our solar eclipse tour for next year. So anybody that hasn't signed up on the sheet but wants to, come see me afterwards. And that's for the total solar eclipse in August of 2017. So we're hoping to put together a little bit of an expedition to go down to Oregon and photograph and observe the eclipse from down there. So we've already got almost 20 people on the list. If you're not on it and want to come on down and see me, we'll put you on the list. And we also now have a proper mailing list for it too, rather than just like a CC email list. And so that's the address there in case you didn't text message. And so, treasurer's report.
Our members account currently stands at $13,098. Our gaming account is at $725. So to put the gaming account in perspective, that's from Raffle ticket sales that we've been doing. We started those up at the West Shore Mall, the Family Festival, and we're selling out to the public there. We had a bunch of tables out there. Many of you here in this room are volunteering, and thank you very much for doing so over the course of the weekend. We had 843 was our count for people who came to our table and actually stopped. And we made $705 in ticket sales, and we sold one of those leftover calendars of Lori's. So the other 3 went as buy 6 tickets, get a free calendar. That's how we got them business. So that's what's going on. March 5th, RASC of Cattle Point will take our last stab at a clear sky after being kind of skunked all year. So that'll be the last one, and it starts early because I don't want it interfering with the summer night Saturdays up the hill. That's it.
Thanks, Bruce, and thanks for putting the hobby show together. You did a really, really good job on that. Somebody ask anything from the board? Okay, Michelle is our VP as well as our librarian. He's upstairs actually getting those books ready and making a coffee and cookies ready for us for later. Chris?
So the membership stands at 218, and there are 13 people in the grace period, which means membership expired either at the end of December or the end of January. If you have any questions, please see me or email me. It for the moment.
Good, thanks. Reg, Sky News.
Hello, everyone. First of all, I don't know if anybody had a chance to see, there was an excellent TV show about Bill Ullman's telescope. Some of you might have captured that. Now, if you want to learn more about his scope and many others, he did a terrific centennial history of the Victoria Centre. And in section 5 of that, he's got a thing called Individual Observatories built by Centre members, and it's really a lot of fun to read. And where you could get it is go to last month's Sky News. On page 6, there's a link to it, and just follow the instructions and you can find it there. So I encourage you to do that. As for the current Sky News, the strange color in this is because we are at the dome at UVic, and they have kind of red lights all around the bottom of it, and so it gave kind of a weird feel there. But we had a great time up there, and if the weather permits, we'll have a great time on this Friday night. One thing on in here is that we have a contribution from our national representative, Lori Rose. Now, if anybody has got an article they'd like to write a story that they'd like to tell about some of their observing experiences, maybe talk about their favorite constellation or whatever, please let me know. I'm the editor at Victoria RASC, and it would be really helpful to have somebody else write something. So I encourage you to think about that. And there is an error in this. Our speaker tonight, Sebastian Lavoie, I said that he was a second-year PhD student, but he's just kind of, the odometer's just rolled over. He's actually now a third-year student. So I look forward to hearing his talk a little later on. So I've got 6 copies of this, so if anybody wants a hard copy, please see me after or during the break, and otherwise it's online. Thanks very much.
Thank you, Rich. It's a good issue.
Very good issue.
So not much else to report on the star party. I did go to the chosen council last week and kind of plead our case for waiving the star party field fee. In past years, they've decided right on the spot. This year, they haven't got back to me yet, but it shouldn't really be a problem. And once that's done, then it's just a matter of being able to be guest speakers, and the star party is on. For public outreach, we still do need a public outreach coordinator to kind of set up and run some of the public outreach events, like the hobby show. We're sort of doing it on a one-by-one basis right now, but it would be kind of helpful to have one person that would take over the other 3 or 4 events that we do in a year. So if you're interested in that, find out, let us know. Summer star party, Lori.
Do you want Sid to talk about the schools?
Oh, yes, cool.
Actually, over the past,
Yes, Sid first.
that's okay. But we have had a busy year this year with the schools. It was quite challenging in a way. It has been for the last couple of times we visited various schools because the provincial government has changed their space astronomy curriculum for the schools, and it had challenged us to come to the level in explaining to age 5 kids recent 4 seasons or moonrise, moonset, and it has been difficult because we are used to presenting our program to grade 3 kids about solar systems, so we knew all about solar system, but explaining that subject to a little kid is challenging, to say the least. We have had busy time, as I said. We visited 48 classes this year, 48, because the Center of the Universe is closed, and so all the teachers want us to go and visit them. And we had 3 night sky games, had to have some cancellations because of the Victoria weather, which we have had this fall. But we are coming this next Tuesday. Let's hope that it's going to be beautiful at Eagleview School. We have enough volunteers to take care of that. You're off the list, by the way. And Galileo moments for the schools is about 1,800, around 1,800. So it has been like 1,800 one day since September. Since September, yeah. And there are 3 more schools to go, and then we are going to say, quick, what the heck, we're going to take this summer break.
Oh, well, very well.
Yeah.
Thanks, Well, Lori, we're kind of all involved in this, so you tell me.
Yeah, absolutely. So the DAO summer Saturdays are really kind of getting have to be really worked on. Last week we had a meeting in which we decided the dates, which I believe start on May the 14th.
May 14th,
And go for 5 weeks until into June. And then we take a little bit of a break for the solstice. And I think it's maybe 3 weeks, 4 weeks off, and take off, and then go for 3 weeks, and then go back in July and finish on August the 20th. And so we've got, I think it's 14 weeks that we're going to be open in total. I think 13. Along with the Astronomy Day on the 14th of May. And I think things are coming along. David Lee, is David here today? Don't see David. David is going to look after speakers. And so we're trying to get like one person from the astronomy community, and then possibly another person from one of us that would give something, a little bit more on what's happening in the night sky and what's going on. So we have a couple of speakers a night. I think that probably is going to be great. We're going to need to have more people trained on some of the different things to do. So we need Aaron is up here in the back, and Aaron is our planetarium specialist. And we're going to, and because he's not going to be here in the summertime, probably not going to be here in the summertime, we're going to need to have some people who are going to be really trained on that machine, the digitarium. Is that what's called, digitarium? And doing the stories, but you actually have to maneuver and manipulate this fancy machine in the planetarium. So it does take a little bit of time to figure that out. So we are looking for people, probably at least 4, right? At least 4 people to be, because it would take 4 people to do what Aaron did. Okay, like, it's just mind-boggling. So we would like for, so if you're interested in storytelling and talking with groups of, small groups of people, well, 25, a squishy group of people in a planetarium. If you're interested in doing that, then please come and see Diane Bell. And we'll get some training done. We're going to see if we can nab Aaron to do some of the training before he leaves, so that we can get that done. And then the other one is to our tours, the tours of the dome. We'd love to have you. So if you're interested, if you're interested in what's happening in the past 100 years, and are interested in giving some of the tours, again, we'd love at least 4 people to be able to do it. It's not just one person doing it all the time. That's an awful lot of work for 1 or 2 people to do that all the time. If we can have several people do that, if Chris is going to do that or something, and obviously you're not responding to me, no, okay. That we want to have some people like people to do that. And then of course we can have people with the telescopes out. More the merrier. People that have some solar capabilities and some of their telescopes. That's awesome, because that was really well done. I think Chris, you always had your telescope up as well, and it's just great for people to be able to see that sun, just even only if it's for half an hour. Then we can see that go down. So I think that's coming. We are looking forward to having the FDAO, which is the Friends of the DAO, have the lease agreement. We have not quite got that yet, but we're looking forward. We're optimistic that that's going to work, and then we'll get ourselves kind of pulled together for that. And that'll be same date, same times as last year, right? We kind of said the 7:30, over the 7:30 up until 11. That seemed to work out. Okay, with another maximum of 250 people on the hill at any one time. And I know that I was one of the people that said, "Oh, come on, let's have more." I was kind of like that. I always liked a lot of people, but in fact, I think the quality of the experience for the people on the hill at keeping it to 250, and so people could maneuver and wander around and not get into some of the things. Because there wasn't room, then I think it was good. So I'm trying to be pulled over to the other side on that one. Is there anything else, Sherry, that we need to do for Summer Saturdays? Just volunteers. I think maybe next month we'll be getting having some sign-up sheets for the Saturdays. If you know that you'd like to do it sometime, and we're not asking people to do this all the time. There's absolutely no way. I mean, none of us are going to be there all 14. Maybe Sherry. I don't know. But we're not asking you to do that. We're saying if you can give even 2 or 3 or 4 weeks in the summertime between May and August, then that would be fabulous. And if you kind of know where your schedule or what your schedule is looking at, then you can do this. We've also got this is for Astronomy Day on May the 14th. So this would be at the museum and up at the hill kind of at nighttime, right? Or
That's pretty much just a daytime.
this is a daytime one, okay. So if you're interested in putting your name down for that, then that would be great. Okay, have you guys have that? I'll put it on here. And can I just talk about this coming Saturday just while I'm up? Sure. Is that okay? So this Saturday night, the 13th, we're going to be having a winter star party. Rather than a summer star party, we're going to have a winter star party. And don't even talk to me about what the weather's going to be like on Saturday. But we're going to try, if it's nice, we'll put up some telescopes. We're having JJ Cavallars, who's going to be coming in and talking to us about what the New Horizon telescope, the New Horizon satellite is doing and where it's going and what's going to happen to it. Maybe show us some of the really gorgeous pictures of Pluto. Because the last time JJ talked to us was at the Astronomy Day last year, before it even hit Pluto, like went by, Pluto passed by. And so we've got some gorgeous pictures. And he's also going to give his ideas about the new Planet 9, things that are kind of on Planet 9. And there are some definitely different opinions that are going around, so we can kind of, as I say, start the debate. So that will be, we're going to be open 7 to 10. Please come up if you would like to come. We have a maximum of 100 people on the hill, but we can do this for this night. So we're asking you to just simply reply to membership@observatoryhill.org. I put that in a little thing for everybody, and just so that we can keep track of the numbers and we know how many people are there. So it's membership@observatoryhill.org, and that's just simply if you just simply reply that you'd like to come, and then we can let you know that you're coming. Okay. Thanks very much, everybody.
Thanks, Lori.
Yeah.
Website, code.
Not much to report. There is a summary of the 2017 books posted on the website. You have to scroll down a little bit on the front page to see it, or you can click on observing.
Thanks, good. Thanks, Joe. And text on that.
The cogs of motion are slowly going with FDAO and RASC partnership to bring internet up to the observatory. This affects us as well as the FDAO because we've never had full internet off the VCO site. I put together a pretty modest proposal that'll make that happen, and it really all hinges on convincing a few scientists that I won't interfere with their RF activities. So far as the website itself, we had just over 1,300 visits to the website with 3,300 and something page views, average of 1 minute 42 seconds total visit time. That's about all I have to say.
Good luck with the internet thing.
Yeah, there's a meeting, I think on the 24th, 2 Wednesdays from now, so
Good luck.
we'll see.
For the visitors and newcomers who don't know, the VCO stands for Victoria Centre Observatory, which is our own little observatory that is on the same hill as the Canadian Astrophysical Observatory. We've been lucky enough to get a land use agreement with the LRC to run our own little observatory, which, if you remember, it came up to use. It's a computerized 14-inch meach with a passive brain and 5-inch refractor notch on the side. We have full imaging capabilities with CCDs, and it's just really cool. So, just one of the benefits of being a member. Yeah. That's a lot of fun. It's really a great thing. But yes, internet's always been kind of a bit of an issue out there. So Matt's done a really, really neat proposal. I can't wait to see why it won't work, but he doesn't have to convince me. It's other people he needs to convince, right? So good luck with that. Thanks, Matt. National issues, Lori.
Okay. So I was talking to Chris, and he says that nothing has come up that's really totally, completely major, right? That's in. But the one couple of things is of course the May long weekend is going to be the big RASC annual general meeting that is in London, Ontario, in association with AstroCats. So it's quite a big thing, a little bit bigger than even what we had here in Victoria for things that are going on. So it's going to be really good. And so everybody is invited to come to that, and buy and sell telescopes and everything, right?
Yeah.
I mean, there's all kinds of stuff there that's much bigger than what we had. Well, we didn't have anything like that here, so that's a whole different kettle of fish. And then the other thing is that the National Board of Directors for the RASC needs to have, they kind of have a 2 or 3 year, is it 2 years, 2 or 3 year?
We have a 3-year term.
3-year terms, and 3 people are flipped over each year. And so there's actually room for 3 new directors from across Canada. And if you are interested in doing this yourself, or if you have someone that you would like to nominate to be a board of director, then there is well, the bulletin had something in it, the national bulletin had something in it, and go on the website to check that one out. And so, or you can come and talk to me, and we can get that kind of organized. I think it's due the middle of March, so it's only got another month to go, because it's not July that we're having, 1st of July we're having the meeting, it's actually now the middle of, or the end of May, that means that everything is being kind of pulled up much faster than it was before. I think that's, and I had a little bit of a thing about tours and things like that in the Sky News, so you can check those out as well. Yeah, thank you.
Okay, thanks, Barbara. Any other new business that anybody wants to bring up? Comments, questions, anything about all of the above? All right, good. Yeah, just a reminder, next meeting is not going to be in this room, it's going to be B150, which is just on the other side of the little kind of lobby here. So remember, next week or next month, if you come here, there's nobody here. That's why, as well, in this room over there. So if there's nothing else, then we'll introduce our guest speaker for the night. Sebastian Leroy is a 3rd-year PhD student. Part of that is his master's in Quebec City and studies the evolution of massive galaxies and clusters. So please welcome Sebastian Leroy.
Thank you. I usually prefer to speak without a microphone. So is it okay right now? Yeah, cool. I probably have a strong voice. Teachers say that we have. I have a cold, so hopefully I'm not going to end up coughing all the time. But we'll see what it goes. Okay. Now I realize that I have a thing on my computer that makes everything looks good. Okay, so first of all, thanks for having me. I was supposed to present at the DAO on a Saturday or something last summer. Right. There was a power outage that day, so now I get to come here and actually talk to you for a longer time. Ask questions or stop me whenever you want. If you have questions during the talk, I'm afraid to be more active. Yeah, that's it. Let's go. So, I'm going to talk to you. I do observational astronomy, looking at galaxy clusters. And what I'm going to talk to you is somewhat related on bigger scales, something called observational cosmology. So how do we understand the evolution of our universe and the structures within our universe? And how did we go through that to build the universe? I'm not going to start very early. I like the historical part of it. Like, scientists are, if we think about the big name scientists like Einstein's or others, they're like heroes or something like that. We kind of point at them because they made revolution in their time. Scientists are the product of their time and their era. And but this is a thing that is kind of changing. It's very interesting when you're in science and you're interested in this history. Is that in the past it is easier to point, say, fingers or name people that are big figures that everyone know about, while since, say, maybe the second half of the 20th century or something like that, science has become so complex that we don't really have the romantic view of science being a genius sitting in front of a candle with his book and doing math and suddenly solving the mystery of the universe. That may have been true and that did happen. That's why we remember some of the big name scientists. But it is a thing that is changing in science, is that through its complexity and its development, the sheer size of it, and there's just more scientists also nowadays. We went from, say, scientists being some sort of rare elite that had the money or the chance to do science, to nowadays a world where it's more accessible, there's way more things, and the developments are, albeit very important, they are maybe slower. We don't specifically expect the next Einstein to be born, although it would be interesting. But hopefully my talk will kind of represent that. So the first part is more about characters. It's important that drama can, like, something to carry my story will be put into the characters here. And the next part is, I think, will reveal the fact that the latest discoveries about the universe have been the result of bigger enterprise, where you can't really name a single person and say they discovered this or that. And because I only have 1 hour, I'm going to skip the very old people. There's the Greeks and Galileo. So let's start 18th century. We already know that the sun is the center of our solar system. And we already have like some knowledge, thanks to Newton, about laws of gravitation. We already know some things. And from there, how did we build this thing? How did we build this thing? That slide here represents, it's actually a result of a simulation. It represents it's like we put all of our knowledge of the universe and its formation and its evolution to create something that evolves and resembles like this. You see a structure made of filaments where, like, all those single dots here would be individual galaxies, assembled in a structure made of like a web and holes and voids and clusters, creating that. But we didn't get there very quickly. And the first part of it is my story. Actually, it is a musical style. And I forgot to bring like a prize or something, but if you can guess who wrote that, you should be getting something. I have to stop it because I really like this specific symphony. Yes, William Herschel is our first big character for tonight. Very good. So this is first movement of William Herschel's 8th Symphony, and he is one of the most interesting scientists ever, I think, because of his path. Like, he didn't start as an astronomer at all, and yet he did such incredible things for science and astronomy. And some things that strictly are placed within the star. So the reason why I showed you that is I actually started as a composer, and by the time, he was actually composing classical music before Mozart was born. By the time Mozart was born, he already had 5 symphonies, and by the time he was 30 or something, or he switched to astronomy around 40 years old, he had more than 20 complete symphonies written, of which I think the number 8 is the best. But yeah, it didn't start as an astronomer at all, but he was the first astronomer later, but his path, music led into astronomy, through the fact that even in those times, that's in the 18th century, we already knew there is some math in, like, building musical instrument, length of piece of string and tension and everything to make an instrument work. And that had just him interested in more than music and how we build those instruments and the math that is behind it. And that just led him to meet more people. And at the time, the big thing was happening is that they were finally able to make much higher quality lenses than what was used by Galileo with his telescope and stuff like that. So he just met people and eventually became interested in optics and lenses. And through that, he met some astronomers until eventually he was convinced that astronomy was actually the thing he wanted to do. So he left music behind. Still, I guess 20-something symphonies is a pretty good pace. There is, if you're interested in that, because Herschel is not a very well-known composer, even though he has more than 20 symphonies. And somewhere, I don't remember the year, but within, say, the last 20 years or something, there's an orchestra in the UK who they recorded, or first, there exists like good recordings of all of his symphonies, modern recordings. They've just reduced them to put them back there. Something I don't know that I would like. At the time, it's interesting in lenses, but the astronomy at the time, the big thing, was not really using small telescope with lenses. Lenses were interesting. But what he wanted to do was the hot topic at the time, which was, let's discover binary stars. And the way you do that is, you actually don't use reflector telescopes. And they didn't have the same quality of mirror we have today, so when he was doing that in his 40s, he would spend hours a day just polishing the mirror because they would get oxidized extremely quickly. That was his life, was polishing mirror and looking for binary stars at night. But one thing that's interesting is that if you look at binary stars, you're going to have a mirror of a certain size, but I think his largest was maybe about 2 feet in diameter. But you don't want a large field of view. You want to like pinpoint stars to be able to discern the binary if it exists. So they were actually extremely long reflector, and they didn't name the telescope by the size of the mirror like we do now. They would name them by, we had a 40-foot telescope, which was the length of the tube. But the point was, so it doesn't give you very useful information, but the point was that they were using those telescopes with large F ratios to be able to discern the star. That was interesting to him, but he wasn't working alone. He was actually working with his sister, Caroline, and she was helping him. So at some point he gave her a gift, which was a much smaller reflector telescope, like something this big, which had a much wider field of view, because the point was that she was supposed to use it to look for comets and stuff like that. And she ended up actually discovering, realizing that there were hundreds of nebulae in the sky. So eventually, Herschel was only interested in binary stars, and when they realized there were so many nebulae, they eventually turned their attention to that. That eventually led to the publication of the general catalog, which had over 2,000 nebulae in it. And when I say nebulae, you'll realize that we don't know that they are a galaxy at this point, but some of them are galaxies.
Sorry, can you turn off the sound?
Oh, yeah, sorry, yeah. I'm just supposed to remember to hear what.
Thank you.
Thanks. Yeah, they eventually published a catalog that eventually was updated to what is now the new general catalog, the NGC catalog that we use, was started by him. He did way more than just that. In 1781, he discovered Uranus. Good. He's also one of the first persons to theorize life on other planets. That's the thing he did. And, going back to Uranus, again, all of those discoveries, product of their time, and we know the planet as Uranus now, but when he discovered it, as a British man, he initially named the star the Georgian star, after King George, who was the king of Britain at the time, and because obviously that didn't work really well with the French only called the planet Herschel. So they gave it a different name. I'm not exactly sure when it was actually officially named Uranus, but that's just a thing, right? They didn't like each other very much. Another thing that he did very much out of nowhere, he was doing tests with prism. So take the light of the sun, go through a prism, and you have a rainbow on the other side. And he wanted to figure out if all colors were the same temperature. That's the thing he wanted to do. So what he did is he take the prism, he puts the thermometer in the red part, in the middle green part, say, and the blue part, and then you need something to compare it to. So you put something next to the red part where he doesn't see any light, And the problem, the thermometer that is past the red light gets warmer than the other ones. Herschel just discovered infrared radiation by doing an experiment trying to figure out if visible light at different temperature, it doesn't, but infrared does transfer more energy to the thermometer and makes it warm. That's just a discovery that he did. And what is more relevant to what we're talking about today is one of the first person who tried to estimate the size and shape of the universe. He did that using a telescope by using a method that was still used until the beginning of the 20th century called star counting. You point your telescope at a region in the sky, and if you assume that stars are vaguely distributed equally, just count the number of stars you can see, and you say, so that's the number of stars that is in this region of the sky. And just create a map of that. And the map that he had is actually this. This is the first map of the universe made by Herschel. We are here in the center. So basically what this is meaning is that if you, in that direction, you saw less star in the field of view of this telescope, in this next direction, you saw more stars. He was already able to discern some disky shape, although it's not extremely precise. And obviously there are stars that you just wouldn't be able to see with his telescope because they're too faint. It is the best result you can get, although it is not the final result. Science is not about getting the absolute truth, it's about getting the best result you can, right? You're slowly moving towards what is truer with you. And then, after Herschel, first hero, well, not much happened for about 100 years. Things did happen, it was just for the dramatic effect, but in terms of describing the cosmology of our universe, few things happen. Now we have to fast forward to our next big booming 20s, like the 1920s.
Those lazy people in the 19th century.
Well, they did all of thermodynamics, statistical mechanics. That's just spectroscopy astronomy was booming in the 19th century. It's just, again, dramatic effect, but it's partially true, specifically about cosmology. They did those things. Okay, fast forward to the 1920s. This is not an astronomy-related picture. The reason is, told you, all of those things are, science has to be taken in context. It doesn't make, it is interesting by itself, but if I stand here and I just tell you about stars, how stars evolve or something, it's a bit too impersonal, right? And it makes it, I think it makes it more interesting to more people if you build something, right? You build your universe around the story you're telling. And the 1920s were actually, specifically the 1920s, interesting because January 16th, this is the start of the great experiment in the United States, prohibition of alcohol, which eventually led to prohibition in some of the provinces in Canada for some time. The League of Nations was established, so the ancestor to the UN, although it's pretty much only known for being unable to stop Germany from starting World War II. We didn't do that much. World population is 2 billion, now we're almost getting close to 8, maybe we've already passed 8 billion or something. That's a lot. That's 2 years after the end of the Great War. The Spanish flu, which is pretty much stuff about like that in the 1920s, killed twice as many people as the Great War did. 20 million people died during the epidemic. And specifically here in Canada, 1920s. The country is only 53 years old. Some people in this room are older than the country would have been in 1920. And it's again, dramatic effect. It's fine. The first airplane. This is not even 20 years after, 15 years after the first planes were flying. The first airplane to fly across Canada arrives in Richmond from Halifax. It's not like a one flight thing. It's like they had to stop on the way, play again, but it's still, that's the first time it's done. And for Star Trek fans, that's the year that Scotty was born. That is. Okay, so that's what the world looked like. That is before the Great Depression, but it's just after the war. So I guess people had hoped that maybe the world would get better, which it did for some time. And then more relevant again to our subject of today, what is 1920 in astronomy? first of all, at the time, the biggest telescope on the planet is the 100-inch Hooker telescope, which is looks like it's made by like a railway company. Very interesting design. If it works, it works. But I really like. The planets at the time were thought to have come from a different star. It was extremely interesting. It's called the Februrary theory, which I'm not sure if they had anything to prove that it may have been the case. But the point of the theory is that the sun was already there with no planet, and a star passing very near it because of its gravity kind of bulged our sun, forcing it to expel some matter around it in a disk that eventually formed planets. This is not how planets were formed, but this was one of the leading theories at the time. The Earth is mostly made of silicium, iron, and oxygen. There was thought at the time also that stars must have been made mostly from the same element. They are not. Stars are mostly hydrogen and helium, and some traces of metals. And the planets like our own are formed of those things, but we didn't know. They didn't know back then. And yeah, they thought that stars were powered by some unexplained, that is before quantum mechanics, that is before nuclear physics. They thought that stars were powered somehow by some quote-unquote subatomic energy, which ends up is true, but they didn't know what it was, or some sort of electron-proton annihilation. At the time, those were the only two particles known. Neutrons were only discovered in 1932. But they did not know that. There's so many things, big changes are open. And as I said earlier, star counting was still used. Because measuring distances, or you can go deeper if you have a bigger telescope and you observe with photographic plate for a longer time, but measuring distances is one of the hardest problems in astronomy, always. And they weren't very good at measuring distance still, so building a better map of the universe than what Herschel was doing was still not very possible. Now bringing back some important characters, those two guys, can you name the guy on the right? Sure, you can name the guy on the left. Eddington is another big character here. So 1920, this is 233 years after Newton's Principia. That's a book he published where he outlined the universal law of gravitation, which basically was like a book of law at this point in science. We still use it. It's not false, it's not working, but it was there. It was a well-known book and everyone was obviously aware of that. But it is 5 years after the publication of Einstein's general relativity. But there is a problem with Einstein's theory of relativity, is that at the time, very few astronomers could do the math that were required. Because the math that are required to do the gravity calculations based on Newton's theory are not necessarily simple, but at the time, people know they were required. If you become a physicist or an astronomer, you have to know how to do it. That's part of your curriculum. The math used by Einstein's theory were stuff reserved for mathematicians, not physicists, not astronomers. So they weren't specifically good at it. Most of them didn't really know what the type of calculations there were. And for having taken courses in general relativity, it is still extremely hard. And it's so we try to bypass it as much as we can, as long as it stays true. But there was a bigger problem than the fact that they didn't know what to do with that, is that the theory was published by a German during the Great War. 1915 was the publication, and the war was 14 to 18. So that's a problem, because first of all, it was published in German. And back then, nowadays, all publications are in English. Back then, the French were published in French, the Germans were published in German, and the British were published in English. The Americans were published in English. But they would have people translating that for specific departments so they can get the information. But back then, the people were just not interested because national pride and other reasons. But this guy here, who was British, he didn't care. So Eddington was working at the Royal Astronomical Society, and he was during the war, he was a pacifist, and yet he was one of the few astronomers on the planet who had the math skills to actually understand Einstein's theory. He became extremely interested in it. He had exchanged letters with Einstein during the war and after the war. And that's actually great because that means that Einstein's theory was still known. Eddington was actually a pretty big name. And he eventually, because of his interest, he led an expedition which led to the first verification of the results of Einstein's theory. Because Einstein's theory wasn't based on observation, it was completely theoretical. And at the time there were no verifications, even though, so you need that at some point to take your theory to the point where people want to justify the word and that and use it. And that happened in 1990, in May, there was an eclipse in the island, a full eclipse visible from the island of Principia, next to Africa, near Africa. And so he led an expedition organized by him and Frank Dyson. And the point was that if you have, I guess which this thing here is showing, you have the Earth and you're looking at the sun. Einstein's theory tells you that the fact that there is a mass of the sun will bend space and time, meaning that the light coming from a star behind the sun will see its path being bent by the sun. So if you take another day of the year, where the same star would be, say, where the path of the light from the star would be not going near the sun, you can determine its position precisely. You can relate, you can then just move it to that date, and you know where the star should be. The star should be visible. The problem is, on every day, on any given day, you can't look at the sun and see the stars next to it that are very close to it because the sun is there. That's why they use an eclipse. Because thankfully our moon is the right size, block the sun, and then you can see the stars next to it, and you can see if they're actually displaced as is predicted by either Newton's or Einstein's theory. And the results were published in 1920s, and that's the first page of their publication, the determination of deflection of light by the suns from observations made at the total eclipse of May 29. And basically here the only part is that the purpose of the expedition, there's so much detail about the specific physical expedition in an astronomy paper. It is very interesting. It's like if I were to make a journal of, I took the plane this morning, blah, 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 when you go do observations. We don't do that anymore, but this is interesting to have this. And here they're just stating the three possible results of the experiments. Either the path of the light is uninfluenced, that means that the star actually does not move, which would be a problem, because even Newton's theory was predicting some movement. Either it is bent by some very, very small fraction as predicted by Newton, or by a value that's about twice as much as predicted by Einstein. And it turns out that Einstein's prediction was the right one. And when Eddington presented the result, Einstein the theory became pretty much mostly accepted, even though it's still hard to do the math. And why is that important? Because this is not about, this has nothing to do specifically with cosmology, but Einstein's theory of relativity, which explains to us how matter and space interact with itself, is the basis of how we understand the evolution of our universe. The universe, which is a big ball of space-time with matter inside it, requires general relativity to understand its evolution. I'm not going to go into the math, but you just need. So by proving that Einstein's theory is right, this is the first step to actually learn to use it to define our universe and its evolution. Now, that's not it. 1920 is actually a crazy year in astronomy. More big drama in science. April 26, 1920 is when an event called, what is now known as the Great Debate happened. And the Great Debate is the Great Debate on the size of the universe. At this time, remember, we're not very good at estimating distances between us and other things. In 1920, the two camps here that are fighting one another are actually going for either the Milky Way is the entire universe, or most of the nebula that we see when we look at them, the same that Caroline the Herschel saw in the small telescope, they are entire other universe. We didn't know the size of the universe at all in 1920. And that is a thing that was solved during the 20s, but the great debate is just, it was a conference in 1920, I don't remember where. And those two guys, Harlow Shapley and Herbert Curtis, actually had, both of them had a talk at a conference, not at the same time in different rooms, where they presented their theory. And basically their point is, I think it is an extremely interesting thing, and just by listening to me now, you will know more. I was surprised by that. You will know more than some of the undergraduate doing a degree in astronomy here, because I surprised them last year when I told them that. Very cool. So, okay, Shapley's side is the one who favored the Milky Way as the entire universe. Shapley is the younger of the two, so he's, I'm not sure what age he is at the time, but he's starting his career while Curtis is older, and already has a pretty good reputation. But they favored the Milky Way as being the entire universe. Why is that? Why is that is actually shown in this image here, which is observations of movement of stars from an astronomer known as Van Manen, which was actually a very well-known and respected astronomer at the time, looking at, that's the pinnacle galaxy, M101, here. And what you see is all of those like tiny arrows is Van Manen saying, I can see, just after a couple of years, I can see those stars move. I tell you, I see the stars move. Remember that all of this, there is a context to it, right? You have a guy who is a well-known astronomer who tells you that he sees the stars moving, okay? In reality, we did, like, for stars to go around this galaxy would probably take 200 million years. We don't expect them to actually be visibly moving over a couple of years, but it's based on an error in calibrating his instrument. But he didn't know that at the time. His results were accepted, and then what this means is that if I see them moving, this thing can't be very far. If it's very far, I'm not able to see that moving. It has to be close, and it's actually a very small object, not a big object, or else it's impossible for the stars to move that fast in relation to the object. That was one of the points. The other one, also based on stuff that we just didn't know, is a nova was observed in the galaxy of Andromeda, so a nearby galaxy, and the nova, here quote unquote, outshone the entire galaxy at its peak luminosity, and they would just not accept that would be possible for a single star. The reason why this is important, the reason why here I write nova, is that they didn't know of supernovae in 1920. Nova are a different kind of explosions. They're basically a white dwarf, so the remnant of the star, like our own sun when it dies. But if you throw some gas at it, eventually that gas can ignite. It's just going to stand on top of it because it's a very massive object. And if there's enough of it, it's going to ignite and burst. Nova are big explosions that often just occurs in like decades or hundreds of years, but they're way less bright than supernovae. So they didn't know of supernovae, and supernovae actually can outshine an entire galaxy. They actually do. They didn't know that. They didn't want to accept it because it didn't work with what they knew at the time. And there were other arguments, but those are some that may have convinced people that which is not specifically unreasonable. On Curtis's side, they favored Andromeda and others, like the Pinwheel Galaxy and whatnot, as other complete galaxies for different reasons. First of all, is that there's actually more novae in Andromeda, novae again, than in the entire, that are visible in the entire Milky Way. Why would they be specifically in that tiny object if it weren't the entire galaxy? That doesn't make any sense. Next, at the time, telescopes were good enough that they could realize that if you look at Andromeda, there are dark lanes here. There are dust in the galaxy. And this is a thing that we knew existed within our own galaxy. So we see structures that exist on large scale in our galaxy, appearing on large scale on that object. So maybe it actually is its own galaxy. And finally, the thing that actually proved to be will prove to be very useful. At the time, spectroscopy becomes better, but it is still extremely hard to get good spectroscopy information on the content of the light of galaxies. But there is one guy, Slipper, who had, at the time, which was maybe the most complete survey of galaxies, which included 5 galaxies. 5 galaxies for which he obtained spectra. The reason why the spectra is interesting is you have the galaxy here, and this thing that you're looking at is, so this is the blue side, this is the red side, and if you can see, if you can identify structure and spectra and follow them, and you saw that the galaxy that looked like they were further away, the structure was moving. That spectral structure, which has a defined wavelength, and a defined color, it happened at a defined color. If you do it in a lab, it's moving with the galaxy. And the concept of redshifting because of velocity was always something that was known. And his point was those galaxies that appear they're farther, even though measuring distance is still hard, look like they're actually moving away from us, which would be quite kind of weird. And those are like thousands of kilometers per second moving away from us. That is intriguing if those objects are really are within our own galaxy, right? And then the debate kind of like stood there for that kind of happened in the year following 1920 until Hubble came to the rescue. Hubble used something that is actually, I guess, revolutionary, because I keep saying that we're not good at measuring distances. Well, Hubble figured out a way to, well, he's probably not the one who discovered it, but he actually used it. At this point, he knew of a way to measure distance very precisely, and this is using variable stars. There's a category of stars that actually are pulsating, so they get brighter and fainter over a period of, depending on the type, can be hours, days, or years. But for Cepheid variables specifically, the time it takes for them to go from peak brightness and back gives you exactly how actually bright they are. And that is extremely important, because in astronomy, if you look at something, you have to know the difference between the actual brightness of an object, and how much light is actually emitted by the object, and what you observe, right? If I take a candle here and I sit next to it, it will appear brighter to me than to someone at the back of the room. So it is important to know what is the actual brightness of the object. And that is what Cepheid variables let you do, even if you're at a distance. If you can follow their light curve, it tells you what their true brightness is. And then you can infer the distance, because if it's further away, it's going to appear fainter. Okay? So you know the actual brightness, and you observe a certain brightness, and because you know both, you just get the distance for free. And that is the concept used in astronomy now, it goes as standard candles. And this is what Cepheid variables were. And what he did is he looked at Andromeda, and he discovered a bunch of Cepheids there, and he realized that Andromeda had to be about 1 million light years from us, which was way bigger than the Milky Way complete universe theory. There was actually an error in the calculations. Andromeda is like more than 2 million light years away, but still, it was too far. And then they could just extend that to other galaxies, and they realized, whoa, those things are actually extremely far. They're much further than the size of our galaxy. We just solved it. Those nebulae, most of them at least, are entire galaxies. So now our universe is much bigger, right? Solar system, or the Earth as the center of the universe. Now we have the sun as the center of the universe. We didn't really know how big was the Milky Way, and now suddenly we realize that we are just one of the others. Of the other galaxies. And what's interesting is that so he wasn't an astronomer by training. He was a mechanical engineer, something. But he didn't publish his results in a traditional journal. He actually published his results first in 1924 in the New York Times. Not exactly sure why, but that's how it happened. And now he just made another layer of drama. So at this time, Curtis is the one who's proven right, and Shapley, so this is Shapley's famous last words, because at the time, he got a letter from Hubble announcing his results, basically telling him, you're wrong, here's why, and Curtis is right. And he was sitting in his office with his PhD student, Cecilia Payne, and she's the one who reported the comments, and this is kind of sad, but this is the way it is. So Shapley goes and say, here is the letter that destroyed my universe. I believe in finding man's result of the disappearance. After all, he was my friend. You know? And it's so deep. This is sad, it's just the way it happened. It's only after that that people redid the calculation of the rotation of the magnetic and discovered an error in the calibration. So for years, he was convinced, Shapley was convinced he was right. It wasn't. And Hubble, well, it didn't stop there. If you can get the distances for one galaxy, you can get distances for a bunch more galaxies. And eventually, this is a figure from a paper in 1929, where it realized that if you get the information of that redshift thing, so you get information that you realize that the galaxies are actually moving away from you, and now you know how distant they are, and you realize that the further they are from you, the faster they're moving away from you. That is extremely interesting and also not predicted, because at the time people didn't expect the universe. They expected the universe to be static. We didn't know about the age of the universe. Some would tell you that maybe it was always there in the same way. Stuff wasn't supposed to move. Kind of back to like the same old. The Earth is the center of the universe, and the planets are orbiting crystal streams on the Earth kind of thing. Everything is static and defined, but this is not how the universe is. And that's where you got this, what we call now the Hubble law, which just tells you that the thing that is further away will move faster away from you. The reason why I say we call it Hubble's law, or is it actually his law? Because he derived that law from observation. But 2 years before that, in 1927, someone who was actually good enough to do the math with Einstein's theory derived the same law completely theoretically. And this guy was Georges Lemaître, who's a Belgian priest, a Jesuit, and he's also known for being the guy who proposed the concept of the Big Bang. This is kind of so interesting that the guy was, and it was true like here and in most countries, that priests or member of clergy were still like in charge of teaching science and math and other things to people in school. There wasn't that big schism or something between the two. That guy was certainly believed in God or whatever, but that didn't stop him for being interested in the science, right? And I guess the concept of the Big Bang is also interesting because it means there is a beginning. And so maybe it's not surprising, but just having that guy who was a priest by formation, but also a scientist who can do extremely complex math is very cool. And the reason why I put the is because technically we should probably be calling it the Lemaître law, because he's the first one who predicted the same form, but he didn't observe it. Okay, so now at this point we get to the point where I've been like giving you big names. Hubble, everyone knows Hubble. Everyone knows, most people know Virtual. People know Einstein. But when we get to a point where I guess astronomy maybe becomes less of a single man pursuit and requires way more complexity. Something that makes it harder for individual geniuses to appear and be in charge of these solutions. Okay. So now there's going to be less big names, and it's going to be about how the view of the universe evolve. Because now, okay, we know there's a universe, we know there's expansion, we don't know much about its structure, we don't know about its age, we don't know about its things. One of the next step that happened is, remember, so we're able now to get distances from galaxies, although it is extremely tedious, but we can do it, but it's obviously getting easier. And what happened next is that if people started to put together large amounts of distances for galaxies, and this is one of the first of such what are called surveys of distances of galaxies. So this is basically just a strip in the sky, and this is the Earth, we are here, and the further you are, well, just distance, or basically. And this is that's the CFA strips, that's somewhere in the 80s, and that's when we started to realize that the universe was not just, first there's a bunch of galaxies, but they're not just randomly distributed. We started to realize that there seemed to be a structure to the universe. here, and like represented by those filaments, although it wasn't very clear at the time. When we started to like see those concentrations and those empty voids, but it's hard, you just need more and more data, and that eventually led to something which is much more modern, which is this, the 2DF galaxy survey. So I guess that's during the 90s, where instead of having 500 galaxies or 100 galaxies, if you put thousands and thousands of them together, what you get, again, here in the center and looking outside, all of those points are galaxies. All of those points are galaxies. And what you see now extremely clearly is that there is actually a structure in the universe. Galaxies align themselves along some sort of filaments and with big cores. And even more interesting than that, if you analyze those things, is that if you take any random piece of the universe, obviously here it's getting fainter because you just don't see as many galaxies because they're too far away, not because they're not there. The universe is the same in all directions. You can take any chunk of the universe and compare it to another chunk of the universe, and it's the same statistical distribution of galaxies. The voids, the filaments. The universe is assembled in some way. We don't know, at this point we kind of knew, but in the 80s we didn't know exactly why or where it came from. And that leads to another thing. If we look specifically at the nodes, the big concentration of galaxies in those filaments, if we zoom in and we observe it, what we see are actually galaxy clusters. Galaxy clusters are amongst the largest and most massive structure in the universe. That's the thing, those are the things I study. Pretty awesome. And you can have millions of billions of masses of solar masses, the mass of our sun, in a single cluster. And most of the galaxies that you see in that image are just part of one single cluster. They range from tens or hundreds of galaxies to thousands of galaxies, and they just all live together in a big sphere, in a big cluster, basically. What is interesting, though, is that they shouldn't. They shouldn't be there. They shouldn't stay in a cluster. We know that they're bound, like our planets are bound to the sun, they're not flying away. But the galaxies, if you look at how fast they're moving inside clusters, they should actually just fly away. We're missing something. We are missing something. And that led to, so that was known way before. In the 30s and 40s, that led to some people theorizing that we were missing something. Some missing mass, unseen mass had to be there. Zwicky, who was apparently a crazy astronomer, was a guy who theorized that first. And that looked at the galaxies like, the only way I can have those galaxies moving this fast stay together is because there's more mass than just the stars I see in the galaxies. That's a problem that stayed unsolved for very, very long. I mean, it was actually not solved because of clusters, although that's where it started. It was solved because of galaxies. Because there's also a problem with galaxies is that galaxies should not exist. If you look at how fast the stars are moving around the center of their galaxy, we're also missing something in galaxies. The stars are moving so fast that they should actually just fly up, yet they don't. Our galaxies do exist, and other galaxies do exist. And it's kind of the same problem, but it's easier to look at a bunch of galaxies and convince yourself that you are actually missing something. If you only have one galaxy, I can tell you it's an outlier. If I have hundreds, which is what they did in the 60s and 70s, they realized all the galaxies, the stars move too fast. There has to be something. That was a convincing argument to say we're missing something, and that thing is dark matter. That thing is dark matter. And the way it was solved, this is a nice video, I think. On the left is how a galaxy should act if there were no dark matter, so that it actually doesn't just fly. And the best way to differentiate the two is if you look at the red dust here on the outskirts of the galaxy. You see they're moving quite slowly. And because the further you go from the center, the slower you should go, or else you fly. On the right is a galaxy is galaxies as they are observed. Obviously the time scale here are millions of years, but if you look at the outskirts, those red points here are moving extremely fast. So stars are not moving slowly. And the way you do that, and that means that the star should actually be flying away. The way you do that is that this one here includes dark matter. And it can be 5 to 10 times more dark matter, although I won't solve the problem for you. I can't explain to you what it is. But we know there is an unseen mass. And there can be 5 to 10 times more unseen mass in the galaxy than there is in actual light from stars or gas in the galaxy. So that's how we observe stars to be, and the only way we can explain it is by dark matter. And ostensibly, dark matter, if we put lots of dark matter in galaxy clusters, we're able to also make them stay together. It is a thing that is everywhere, and you know there's actually more dark matter in the universe now than there is normal matter. Although again, we can't explain what it is.
Does that mean that the stars in the arms are moving at the same speed as the stars in the core of the galaxy?
Pretty much. Well, you kind of have, they go, the ones very close to the center don't move very fast, but you kind of peak, and then they all move at the same velocity. So our sun, for example, goes around the center of the galaxy at about 200 kilometers per second. If we go further or somewhat closer to the core, they kind of all move in that direction. At the same velocity. So it's kind of that the problem is that they're not getting slower, and that would mean that they shouldn't stay there. But if you add more matter distributed everywhere, dark matter, then you can actually have that work and produce that. Thanks. So now we have we've solved dark matter. We haven't solved dark matter. Hopefully we'll understand at some point what it is. But that's it for dark matter. Another big discovery that was important for astronomy came in, I guess, in the 60s. And this is the discovery of the cosmic microwave background and everything. This just had a very funny anecdote to this, and that's why I say how our universe was mistaken for pigeons. So this happened at, so the cosmic microwave background is a remnant that we observe and one now will exist from early days in the universe. When the universe was extremely young, it was extremely hot and it was extremely dense. And it was actually so hot that the only content of the universe was not atoms like we know them, with nuclei and electrons moving around it. It was just a soup of protons and electrons mostly. The problem is in a soup like that, you can, if you're light and you try to move, you just hit something and you don't do anything. So you don't have propagation of light in an early universe that is extremely dense and hot. But there is a time when the temperature of the universe drops below what is about 10,000 degrees. And when that happens, you can start actually taking your protons and your electrons and combining them and forming hydrogen. Then they can just do that. And when they're in their atomic form, they don't specifically block light, or they block light way less, so light can actually propagate. So the cosmic microwave background, which is the kind of an interesting thing, is the remnant from that time when the universe became just crossed that threshold, became cold enough so that everything could combine. It happened somewhat quickly, and as it happened, it just emits light. So suddenly, light can travel throughout the universe, and that's why we see cosmic microwave background everywhere, because it happened everywhere at the same time. And this is, and that light is still moving through the universe. And all happened everywhere at the same time, so even if you expand the universe, that light is still moving, because now it's free to move. But the way it was discovered in the 60s was because of those two guys, Penzias and Wilson, working at Bell Labs on some astronomy and communication experiments with that specific antenna here. Yeah, the cosmic microwave background was predicted before it was actually observed, which is sometimes doesn't happen. And in '64, those guys were doing observations with that antenna, and there was a problem. There was a background noise that they just couldn't bring down. They just wanted to clean the signal, like very high level, like pure quality of signal, but the background was still there. So they tried everything, rewired things, and eventually went into the antenna and cleaned it because some pigeons were living in the antenna. And so basically the antenna was covered in pigeon poop and pigeon. And they, at some point, they actually thought, oh, that must be it. It's the only thing we haven't checked, right? We should smooth the pigeons out of the way. Then they did, and the signal was still there. And this is how the cosmic microwave background was discovered. They eventually, they were electrical engineers. They didn't specifically know about astronomy theory and the theory of the CMB in 48, but eventually, talking to people, someone told them, maybe you should read that paper. And they eventually got a Nobel Prize for the discovery of the cosmic microwave background. And we sent satellite in space, and that is the latest map. I guess this is the map I'm playing from a couple of years back. And this is what the universe looks like if you look in any direction. It looks like this. And this is the light from that epoch when light could actually start traveling through the universe because it became colder. And the reason why this map is interesting, although we see variation in blue and red, those are basically temperature. The difference in temperature between the blue region, which is colder, and the red region, which is warmer, is a couple millionth of degrees. Basically, the surprising thing is that the universe is the same, mostly. We kind of exaggerate it because the interesting thing are those tiny, tiny differences. But the universe is mostly the same temperature at this time. But in the universe, and I'm going to close a loop with the next one. You'll see there's a point of this. Let me show you this slide. At scale of the universe, the thing that dominates evolution of anything is gravity. Gravity acts on long distances, and you don't need much difference in density or whatever to have a change in gravity. What this is telling us is that some regions of the universe are colder and some are hotter. It's like a hot air balloon. Why does it fly? It's because the air inside it is less dense than the air surrounding it. So the matter, so this is just telling us about temperature. The matter that is here is hotter and slightly less dense, even though it's very small difference. And here it's colder and slightly more dense. If it's slightly more dense, gravity likes that. It means that it can collapse. It's easier for it to collapse than the region that is warmer and that is less dense. And what this does, so basically, we get to a point where with that, this is a simulation, which I shouldn't have simulation movies in an observational cosmology talk, but we'll just start. And basically what this does is if you start with tiny variation, this just consider this represents the matter in the universe. And as time proceeds, you have time since Big Bang, so we're going through time. And because of those tiny differences in density of matter in the early universe that we can see in the CMB, structures can collapse. Voids are created where it is less dense. And here you see it becomes denser and denser. And you actually form the filamentary structure of the universe that has been observed in the 80s. So those subjects are kind of different, but they help understand the same story. Yeah, so now, there's a couple more slides. Now we have the universe. We went from counting stars to trying to figure out how big is our galaxy. We then, years later, realized that our galaxy is not actually the only one. There are hundreds of billions of galaxies as far as we know in the universe. And not only that, but we know that they are arranged in a specific structure. Why would that be? That could be like a talk specifically about why it happened. Why would that be? Well, eventually we observed this CMB and we realized that the young universe was actually not perfect, had variations in it. And those variations are what enables the universe to evolve those structures as being. All of this kind of makes sense. There's a much more recent discovery, and that is that the universe is not only extending structures inside it and everything, the extension is also accelerating. It's going faster and faster instead of slowing down, which kind of interesting because when I was a kid, it wasn't that long ago. Okay, but when I was younger, before all of the big surveys, and looking at maps of the cosmic microwave background can actually give you a very good idea of the actual age of the universe. When I was young, and I remember reading those books, I was maybe 12 or something, we didn't know how old the universe was. We thought that the universe was between 10 and 20 billion years old. and we didn't know what the future, the most probable future of the universe was. Remember, all of this is the space-time of the universe, with matter inside of it. So it's not unreasonable to think that if it's expanding, maybe it's slowing down because the matter is gravity and it's pulling the universe. Maybe it's slowing down and eventually it will collapse. Or maybe it's not. Maybe it's exactly perfectly tuned so that it's going to expand forever, but just slowing down and never collapsing. Or maybe there's something else. Maybe the universe will expand faster and faster. We didn't know specifically which one was the future of our universe when I was a kid. Now we kind of know. But the reason why this is important was like those future of the universe is that Einstein himself, when he produced his theory of general relativity, was a fervent, like he really was for a static universe that always existed and would always stay the same and was not expanding, and then realized that it's expanding. He actually added a constant in his equation just to make his universe not expand. His equations by themselves, the original ones predict the universe is actually expanding. The ones that George Lemaître used to get the Hubble law, theoretically. But Einstein added a new constant because he wanted the universe not to expand. He didn't want to think that it was. And actually, it turns out that we do need, the universe is expanding, but we do still need this constant, we call the cosmological constant, because this is the thing where we put that it's even less well known what it is than dark matter. It's dark energy is the reason why the universe is expanding faster. Dark energy is weird, and you can imagine it as a force that pushes outwards. But the problem with dark energy, and the reason why it's causing the universe to expand faster and faster, is that space is expanding. But if I double the space, you would expect, like, say I had like a pool with water in it. Take the same water and I put it in. If I double the size of the pool, you expect the water level to go down because there's as much water. Dark energy doesn't work like that. Dark energy is weird because if you double the size of the pool, the level stays the same, so you just have more dark energy. It has a problem because it's a force that pushes outwards. So as the universe expands, it's pushing harder and harder to expand the universe even more, which is kind of very, very strange. It is also not explained. We know it's there. We know there is such a thing. And because we can see the acceleration of the expansion of the universe, and that actually led to a very recent Nobel Prize. Discovery is from 1999, but what the guys did is they looked at supernovae. Supernovae, like the stars that Hubble used, are standard candles. At least a type of supernovae are standard candles. In that the brightness that they reach is proportional to how long it takes for that to get there and back. Okay, so they're going to get brighter when they explode and then down, and the time it takes for that to happen gives you how actually bright they are. But the thing is, supernovae are the most luminous event in the universe, or pretty much. They can be as bright as an entire galaxy, but concentrated in a tiny, tiny dot for the time that they exist, so you can see them at extremely large distances. And this image I really like because I'm the one who took it in 2011. I think it's probably a similar setup as you guys said. You said you had like a 14-inch with CCD and everything. So I did that with like a 16-inch telescope. I wasn't undergrad at the time. We just had like 2 or 3 astronomy crazy people who were just like, what? There's a supernova at 151, quick, to the dome. And then we just took a couple of pictures. And that thing here, it's not a star, it's the supernova. It's a thing that didn't exist before and was there for a couple of days. And it is extremely bright because you can see them so far back. And if you know their exact distance, you can infer the fact that the distance is not right. It shouldn't be there. And that's how you get the fact that the universe is accelerating. And then let's bring that all back together. The universe in one slide. I'm sure you've seen that image. I tried to not use it because it's there. So here's this one. So kind of have a story now. So we have our big heroes who, they were kind of looking from here. They were looking from nowadays, trying to extend their knowledge on the other side, towards the outside. For the history of the universe, I didn't talk at all about the inflation that would be a talk in itself. All of those could be taught in themselves. At some point in the young universe, after 400,000 years, approximately, that's when we have light starts traveling. Light starts traveling, and we have the cosmic microwave background, which keeps within it the structure of the early universe, which had some over-densities and under-densities. Those over and under densities evolved into the structures that we see that form our universe. The filaments, the galaxies, the clusters, all those things. And our planet and our galaxy. And then we realized at some point, the universe was actually, its expansion was slowing down up to a point, but then dark energy took over because it was actually big enough to compensate for that. And then we just know that it's expanding faster and faster. The end of our universe, it's not going to be what used to be called a big crunch, where everything comes back together, but it's going to be, cold death or something, because everything will get so far apart because of the expansion of the universe. And those are I think the most important pieces of what observational cosmology is and what it tells us about our universe. But in that last slide, there are exciting times ahead. There's always more questions, right? There's always new things, new frontier, and I think the very most interesting thing for me as someone who is PhD is all of the new facilities and instruments that will become available. And they are not useful for astronomers, right? Something like Hubble Space Telescope, right? Kids, or I'm sure there's like, when I was a kid, I looked at the images and you're like, mind blown at what the universe looks like. And that is a knowledge that is fun and available to everyone. Those things do more than science, and they should, because they're paid for by public funding. And the next big thing is, there's actually three next big things. The first next big thing, which hopefully will be launched in 2018, is the James Webb Space Telescope. That's going to be the largest telescope in space. It's supposed to be replacing Hubble, although it does more infrared and optical observations. A mirror which is more than 6 meters in diameter. Now, I don't know exactly how big 6 meters is. I should have tried that before you guys were here. But it's big. It's big. And Hubble is 2.4 meters. So Hubble would fit in like a corner here. And hopefully what this will enable us to do, one of the goals is that because of its size and its position, it can hopefully look for the light of the first stars. Because at some point we have to start forming the first stars. Hopefully this is one of the things that this can do. Other exciting thing is here I put the 30-meter telescope, although you probably know that the construction is on hold right now because their permit is revoked. I'm sure that's going to be solved eventually. But in general, it's the concept of the new 30-meter class of telescopes. The Europeans are building 30-meter class telescope in the south, and they don't have problem with their construction. So hopefully around 2025, those should come online. And 30-meter is a huge telescope. Like the biggest at the moment is about the order of 10 meters. 30-meter is it's 25 times the size of the mirror of the James Webb Space Telescope. It's on the ground, so you have to like deal with the atmosphere, but there are people actually here, well, at UVic and up the hill at HIA, who are working on an optic system to correct for that and eventually get picture quality, image quality that would be way better than what you would get even from space, and the sheer size of it lets you do incredible things. And interesting thing, Canada's contribution to the project, maybe you already know, but it's actually been done. That was like $200 million, I think. And it's going to be built in Port Cook with Lebanon. So eventually, at some point, I'm not sure if we can visit, but maybe we can visit the facility where they actually build it up. And the one that you should actually be looking for, and maybe actually wait early tomorrow morning, is LIGO. You've probably heard of it, maybe, but there's been rumors for like weeks or months in the scientific community. LIGO is that big thing here with 2 tunnels, and it was a facility built in the US to detect gravitational waves. Gravitational waves are a thing that is predicted by Einstein's theory of relativity. Einstein's theory has been right pretty much all the time since it was discovered. What people are expecting, there's a press conference tomorrow, it starts at 7:15 a.m. There's supposed to be an announcement, and because of the rumors that were going around, we really hope that what they're going to announce is that they've detected the first sign of gravitational waves. And like, we're talking about crazy events in the universe, because to detect, this is like the first ever the big scale, large scale detector for that. So it's not super sensitive. The thing we could detect is 2 black holes, for example, spinning around one another and merging. That produces a ton of gravitational waves. That's the kind of incredible events that this thing could detect. And if they indeed detect gravitational wave, there's 2 things. First of all, they get the Nobel Prize next year, probably, and or soon. And also that opens an entirely new method of observation for astronomers of the actual universe. Because looking at gravitational wave, it's kind of impossible even to imagine what the universe looks like in gravitational wave. But hopefully, if it's true, then that means more funding for that gets an entirely new window into the universe that thing gives us. So if you're interested, at least if you don't wake up early enough, it's sure it's going to be all over the internet tomorrow and during the thing. Look for that. That's it.
Thank you.
Time for questions?
Yeah.
Any questions?
Will there ever come a time where dark energy will override dark matter and cause?
It actually already is.
Well, that's between galaxies. How about within galaxies?
Yeah, so technically, if the expansion is fast enough, there would be a point where, so in the universe, every information or anything that happens is communicated via photons, or that kind of thing, which has a limited speed limit, right?
Yep.
And the thing that can happen, I think, although you're like hopefully making up a good answer, is that technically, because of the universe expanding faster and faster, you can get to a point where if you have 2 particles that somehow are exchanging information about themselves via light, you can get to it, but the space between them is increasing, and it's increasing faster and faster. You could get to a point where it expands faster than the speed of light. That's the weird thing about the universe, is that nothing inside the universe can go faster than the speed of light, but the expansion of space itself is not specifically limited by the speed of light. So yeah, you could get to a point where the stuff inside galaxies are not able to, or even like gravity is not able to tell something like, hey, I'm pulling it or something like that. Maybe, but that's not an expert on that. That would be my opinion.
Any other questions? All right. Thank you for coming.
Oh, I got a t-shirt.
Thanks. Okay, don't forget, free coffee, cookies, and books in the astronomy lounge upstairs. If you don't know where that is, it's upstairs in the